Alright guys, you had the 2008 number 1 problem for homework, so I want to work through this one. We have a reaction of carbon plus carbon dioxide forming 2 carbon monoxides. We're told that solid carbon and carbon dioxide gas at 1160 Kelvin were placed in a rigid 2.00 liter container, and the reaction represented above occurs. As the reaction proceeds, the total pressure in the container was monitored. When equilibrium was reached, there was still some carbon remaining in the container, results are recorded in the table below. There we go. Okay, so we have our table, we have our time. As time is progressing and we watch our total of gases, notice that it tells us that some of the carbon remains, and we're at equilibrium, so we can kind of assume that all 3 things are going to be present. So this total pressure is going to be a combination of all of our gases in the system, which includes our carbon dioxide and our carbon monoxide. So kind of keep that in mind as we're working through this. Okay. First thing it tells us to do is write the equilibrium expression, Kp. Easy peasy, right? Big thing with Kp is, remember, you have to show pressure. You cannot use your brackets. And again, it is still products over reactants. So the pressure of carbon monoxide raised to its coefficient, which is 2. Okay. Over the pressure of carbon dioxide, which is just to the 1, since the coefficient is just 1, and this guy is already balanced up here nice and pretty for us. Okay, so easy peasy. Moving down. It then says to calculate the number of moles of CO2 initially placed in the container, assuming that the solid carbon volume is negligible. So let's go back up here and kind of see what we know. Okay, so first off, carbon dioxide initially placed, so this is before any reaction occurs. We're told our temperature, we're told our volume, and we are actually told our initial pressure way down here in our data table. So at time 0, that is initial. So we've got P, we've got V, and we've got T. And of course, we already have R, so we're going to use our PV equals nRT. Okay, so PV equals nRT, where pressure is 5.00 atms, times a volume of 2.00 liters, and you can go back up and grab that from the top if you want. N 0.0821, and where we're told a temperature, I believe, is 1160. It is. And that's already in Kelvin, so be careful with that. So we go through and actually do this math. So we get 5 times 2, which is 10, divided by 0.0821. Okay, and we're going to get a mole value once we do all this of N equals 0.105 moles of CO2. Okay, so step B, or question B, easy peasy, moving on. For the reaction mixture at equilibrium at 1160 Kelvin, the partial pressure of CO2 is 1.63 atms. Calculate the partial pressure of carbon monoxide. So, first and foremost, we have to recognize that this is an equilibrium problem. And if you remember back to equilibrium problems, what was our go-to? How did we solve these problems? Well, we used our ICE table, so we come back up here and grab our reaction. So carbon plus carbon dioxide going to 2 carbon monoxides. We'll transfer that down here. And this is gas. Okay. And we do our ICE table. So ICE, remember initial, change, equilibrium. We don't care about the solid because we don't ever care about solids at equilibrium. We only care about gases and aqueous solutions. We're told initially our pressure of carbon dioxide is 5.00. We got that from the original table, 0 here, which means we automatically know it's shifting towards our products, and that's going to be 2x. So we end up with 5.00 minus x and 2x. And now we stop and go, what do we do from here? Well, we're actually given some pretty nice information. We're told that the carbon dioxide is 1.63 atms at equilibrium. Okay, so 5.00 minus x equals 1.63. And we can solve for x using this equation. Okay, so we get 5.00 minus 1.63, and we get x is equal to 3.37, which means 2x is going to be equal to, that times 2, 6.74. Okay, so that means the partial pressure of carbon monoxide at equilibrium is 6.74. Now there's actually an easier way to do that, which is our total pressure equals our partial pressure of carbon dioxide plus our partial pressure of carbon monoxide. So you could have done this too. Whereas if you go back up, we're given our equilibrium pressure is 8.37, and that's our total pressure, 8.37. We're then told our partial pressure of carbon dioxide is 1.63, okay, plus our pressure of carbon monoxide. So if we do our subtraction here as well, what we'll get is the pressure of carbon monoxide is equal to 6.74. So either one of these methods will work. Again, the beauty of a lot of the AP problems is there are multiple ways to solve it. So you can do it using an ice table, or you can use it doing our total pressure. Now from here, we're asked to calculate Kp. Okay, well, we know Kp, if we go back up to our earlier problem, we're told it is the pressure of carbon monoxide squared divided by the pressure of carbon dioxide, which we just calculated those values. We were told that our carbon dioxide is 1.63, and we're told we have 6.74 for our carbon monoxide, and of course that's going to be squared. So 6.74 squared divided by 1.63, and we are going to get a Kp value of 27.9. Okay, so pretty straightforward so far. Moving on to part D. So first and foremost, we haven't talked a lot about catalysts, but we have mentioned them a little bit. And many of you took AP Bio, so you already have an idea what an idea of a catalyst is. And we will come back and talk about catalysts when we get to kinetics a little bit later once I am back from maternity leave. But I feel like this is a question we can answer based off of what we know about Le Chatelier's already. If a suitable solid catalyst were placed in the reaction vessel, would the final pressure of the gases at equilibrium be greater, less than, or equal to the final pressure of the total gases at equilibrium without the catalyst? Justify your answer. Assume that the volume of the solid catalyst is negligible. So let's kind of backtrack that and talk about what a catalyst is. Let's see if we remember what a catalyst is way back from AP Bio. Okay, a catalyst is anything that is going to allow for the reaction to essentially speed up or move at a faster rate. Now, the way it actually does that, we'll talk about in kinetics, but it's because it's creating a new mechanism. And what we need to know is that a catalyst will not affect equilibrium. It will not affect how much stuff reacts. Remember, the only thing that actually changes our equilibrium position is temperature. And a catalyst is not going to affect temperature. Okay? So with that in mind, what does a catalyst do to equilibrium? It does nothing. It does not affect where equilibrium occurs. It affects how quickly equilibrium is reached. So it's kind of like if we think equilibrium is a finish line, and you have people running to that finish line, when they reach equilibrium depends on a catalyst or whether a catalyst is present. But the fact that equilibrium is present at this point in time, or the finish line is here at this point in time, isn't going to magically change just because they're reaching it at a faster rate. So catalysts affect the rate or speed of the reaction. Remember, equilibrium is when the rate of the forward equals the rate of the reverse. So it's going to get to equilibrium quicker, but what is defined as equilibrium, which is our Kp value of 27.9, isn't going to change. So the amount of gas present at equilibrium is going to be the same. It's not going to be any different whether we have a catalyst or not. The only thing that will make it different is if our K value changes, and the only reason our K value changes is if temperature changes. Okay, so again, maybe a little bit out of our league right now, but something I want just kind of to preface and talk about, because we will be talking about kinetics a little bit later this semester as well. Whoop. Sorry about that. Not sure what my computer's doing. The last thing, in another experiment involving the same reaction, a rigid 2-liter container initially contains 10 grams of carbon plus carbon monoxide and carbon dioxide, each with a partial pressure of 2 atms at the 1160 Kelvin. Predict whether the partial pressure of CO2 will increase, decrease, or remain the same as the system approaches equilibrium. Okay, well, so equilibrium problem. Let's just go to our handy-dandy ice table and see what we come up with. So we have our reaction. Hasn't changed. We've got our same temperature, which means our K value is our 27, I think it was 0.9. Yep, 27.9. That hasn't changed because we're at the same temperature. We're told we have the solid, but we don't care about the solid. Don't let that fool you. Okay, we're told that carbon dioxide and carbon monoxide are both at partial pressures of 2.00. So now we hit that stuck point. Which way is X going? Are we going to be adding X to carbon monoxide side, or are we going to be adding X to our carbon monoxide side? Well, let's see if we remember how to do this. Remember, this is where we compare Q versus K, because we don't know which direction it's actually going to shift. So we calculate Q, which, remember, is the same exact equation as our K value. The only difference is we can't call it K because we don't know if it's at equilibrium. So we have this information, and we're going to plug in our values of 2 squared over 2, which of course gives us 2 times 2 is 4, divided by 2 is 2, so we get Q is equal to 2. Well, how does Q and K compare? Well, K is significantly greater than Q. Well, what does that mean? Remember, K is products over reactants. Okay, and if it's products over reactants, if our Q is too small, what that means is our numerator is too small or our denominator is too big, one way or the other, which means we're going to get a shift towards our products. And remember, we can also do that by putting K and Q in alphabetical order and turning our greater than or less than sign into an arrow. It also tells us which direction it's going to shift, so in this case towards the right or towards the products, which means we will be creating more carbon monoxide. Basically, it's favoring products according to our K. We don't have enough products present, so Q is going to shift towards products to be able to get to K. So we actually end up with a minus X and a plus 2X here. So what does that mean? Predict whether the partial pressure of CO2 will increase, decrease, or remain the same. Well, CO2, we're losing some CO2, and it's shifting towards our carbon monoxide, so that means CO2 will be decreasing. And of course, the reason for that prediction with our calculations, which we can kind of see here, the calculation is with Q, and we would simply say Q is less than K, therefore it's going to be shifting towards products or using reactants one way or the other, therefore carbon dioxide will be being used, and therefore decreasing in pressure. Okay, so hopefully this is helping. Again, just let me or Mr. Christie know if you have any questions, and we'll see you again soon. Thanks, guys.